Welcome back. In this video, we're going to look at examples of graphing polar equations. Let's get to it. All right, so here's our first example. In the beginning here, we're going to focus on graphing some very basic polar graphs, but as we continue through this video, we're going to look at more and more complex polar graphs. All right, and so first up, we're going to be sketching the graph of these two polar equations. We have r equals 3 and r equals -2. And you'll see that on the side here, I'm going to call this my sidebar, I'm going to have our different basic polar graphs for us to reference. In this case, you can see that when we have a polar equation of r equals some constant a, that's just going to be a circle centered at the origin of our polar coordinate system, where that circle has a radius of a. So in this case, we have r equals 3. So what that means is that this polar equation represents a circle centered at the origin of our polar coordinate system with a radius of 3. Now, if we assume that each of these concentric circles represents an increase in the radius by 1, we would say that this first circle is a radius of 1, this second circle is a radius of 2, and the third circle is a radius of 3. Then we can graph this polar equation, r equals 3, and it will look something like this. This circle that we just drew is centered at the origin and has a radius of 1, 2, 3, all the way around the circle. This is the graph of r equals 3. All right, now let's graph our second equation here. We have r equals -2. Note that when you're graphing a polar equation where you have r equal to some constant, that if it's negative, it's not really going to affect the graph of that polar equation. r equals -2 is the exact same as r equals +2. It's just going to be a circle centered at the origin with a radius of 2. So in this case, if we count our circles, 1, 2, this circle right here is a circle with a radius of 2, and so our graph for r equals -2 will look like this. All right, that is our graph for r equals -2. And so that's it for this example. This is a very basic case of graphing polar equations. We just had r equal to some constant, so in each case you just look at the absolute value of that constant, and that is going to be the radius of your circle, which will be centered at the origin. All right, so next up we want to sketch the graph of these two polar equations. We have theta equals 2 pi divided by 3 and theta equals -pi divided by 4. Now these two polar equations are also going to have very basic polar graphs. They fall into this category of a basic polar graph where you just have theta equal to some constant. In this case, that constant will be an angle. And so when your polar equation is theta equal to some angle, you're just going to have a diagonal line at that angle in the coordinate system. So in this case, let's start with theta equals 2 pi divided by 3. If you look at our polar coordinate system here, where would an angle of 2 pi divided by 3 be? Well, since it's a positive angle, we are going to measure it above the polar axis, not below. In other words, we're measuring in the counterclockwise direction. And 2 pi divided by 3 is 2/3 of the way to pi. So we're not going to be going past pi, right? Our angle is going to stop before that. But where exactly will it be? Well, if we divide this half of our polar coordinate system into thirds, I would say that this angle right here is pi divided by 3, this angle. And that means that another third would take us to about here. And so I'm going to say that that angle is 2 pi divided by 3. All right, so from the polar axis to this angle, that's about 1/3 of the way to pi. And then from this angle to this angle would be another third, so 2 pi divided by 3. And then from this angle to pi would be another third, which would take us to 3 pi divided by 3, or just pi. So this angle right here is 2 pi divided by 3. That is where theta is equal to 2 pi divided by 3. So what that means is that for all values of r, the angle is always going to be 2 pi divided by 3. So our graph will look like this. We're just going to have a diagonal line along that angle of 2 pi divided by 3. That is theta equals 2 pi divided by 3. Now for our other equation, we have theta equals -pi divided by 4. So if we want to sketch the graph of this equation, we have to determine where this angle of -pi divided by 4 is. Now it is a negative angle, so we're going to start at our polar axis and measure below it in the clockwise direction. And pi divided by 4 is halfway to pi divided by 2. So in the positive direction, that would take us to this angle right here. This angle is pi divided by 4, which means if we're going below the polar axis, that will take us halfway to 3 pi divided by 2. So that will be this angle right here, and that angle would be 7 pi divided by 4. because 8 pi divided by 4 would be 2 pi, and that would make a full circle. And 7 pi divided by 4 is pi divided by 4 less than 2 pi, or 8 pi divided by 4. So this right here would be our angle of negative pi divided by 4. So our graph for theta equals negative pi divided by 4 will look like this. We'll have a line that goes along that angle all the way to the other side. This line right here is our line, or the graph, for this polar equation, theta equals negative pi divided by 4. Alright, so next up we want to sketch the graph of these polar equations. We have r equals 2 times secant theta and r equals negative 3 times cosecant theta. Now both of these polar equations represent some basic polar graphs. And so if you take a look over at our sidebar here, whenever you have r equal to some constant a times secant theta, you're going to have a vertical line that passes through that value of a along the polar axis. And when you have r equals some constant a times cosecant theta, you're going to have a horizontal line that passes through that value of a along the vertical axis, where theta equals pi divided by 2. So in this case, if we start with our first equation here, we have r equals 2 times secant theta. This corresponds to this graph right here, r equals some constant times secant theta. Our constant a is 2, so what that means is that the graph of this equation will be a vertical line that passes through the value of 2 on the right side of the vertical axis. So if we're counting our circles here, I'm going to say that this first circle represents a radius of 1, and this second circle represents a radius of 2. If we label them 1 and 2, the graph of this polar equation will look like this. We're just going to have a vertical line that passes through that value of 2, and that's it. That is the graph of r equals 2 times secant theta. But now for our second equation, we have r equals negative 3 times cosecant theta. That's not going to be a vertical line, that's going to be a horizontal line, right? When we have r equals some constant a times cosecant theta, that's going to be a horizontal line that passes through that value of a. However, in this case our value of a is negative. We have negative 3 times cosecant theta. So instead of our line being above the polar axis, we're going to need to reflect it to the other side, below the polar axis. All right, so if we go to our graph here, this first circle is a radius of 1. So that means that the value of 1 would be here, and then our next circle would represent a radius of 2, and then the third circle represents a radius of 3. So if our value of a was positive, if this was positive 3 times cosecant theta, our graph for this polar equation would be a horizontal line that passes through that value of 3 along this vertical axis. We would be above the polar axis, but since it's negative, we need to reflect that to be below the polar axis. So if we're counting our circles, we have a radius of 1 here, a radius of 2 here, and a radius of 3 there. So our graph is going to be this horizontal line right here that passes through that value of 3 below the polar axis. This is the line or the graph that is represented by this polar equation. So next up, we want to sketch the graph of the polar equations. We have these two polar equations of r equals 2 times cosine theta and r equals negative 4 times cosine theta. And so this is a different type of polar equation. In this case, if we go to our sidebar, those two polar equations fall under this category where we have r equal to some constant a times cosine theta. And when your polar equation looks like this, you're going to have a circle with a diameter of a that rests on the right side of the vertical axis and is split by the polar axis. All right, so in this case, for our first equation, where we have r equals 2 times cosine theta, our constant a is 2, so that means that this equation represents a circle with a diameter of 2. All right, and because it's r equals 2 times cosine theta, that means that our circle will be on the right side of the vertical axis, and it's going to be split by the polar axis. So if we go to our graph here, a diameter of 2 will take us out to our second circle, if we're saying that each circle represents an increase of the radius by 1. So I'll just label that. This is 1, and this is 2. What that means is that our circle will look like this, right? It's on the right side of our vertical axis. It is split by the polar axis, and we have a diameter of 2. This circle right here is the graph of this polar equation. Now, if we look at our second equation here, we have r equals negative 4 times cosine theta. This is also going to be a circle, just like this one. However, our value of a is different. We have negative 4. So not only is the diameter going to be different, but we also have to flip or reflect our circle to the other side because that value of a is negative. When your value of a is negative, for either one of these basic polar graphs, even if you have sine, if that value of a is negative, you would flip this circle to the other side as well. But we'll get to that in the next example. When that value of a is negative, you need to reflect your circle from where it normally would be. All right, so in this case, if we're ignoring the fact that this value of a is negative, if this was positive 4, our circle would be on this side of the graph with a diameter of 4. We'd go out to the fourth circle, right? If I label these, we have 3 and then 4. However, the circle will not be on this side because it's negative 4, so we will reflect that circle to the other side of the vertical axis. So if we count our circles on the other side, we have 1, 2, 3, 4. So the graph of this polar equation will look something like this. All right, we have a circle with a diameter of 4. It's split by the polar axis, and it's on the left side of the vertical axis because that value of a is negative. Okay, so that is the graph of that polar equation. All right, now let's look at another example, but instead of having equations where we're working with cosine times a constant, we will look at polar equations where we have a constant times sine. All right, so here's our two polar equations. We want to sketch the graph of them. We have r equals 3 times sine theta and r equals negative sine theta. All right, so in this case, these two polar equations fall under this category where we have r equal to some constant times sine theta. And when you have a polar equation like that, it's going to represent a circle that rests above the polar axis and is split by the vertical axis. And it will also have a diameter of that value of a. Okay, now if that value of a is negative, then of course you need to reflect that circle to be below the polar axis instead. All right, but let's start with our first equation here. We have r equals 3 times sine theta. If we graph that, note that our value of a is 3, so we're going to have a circle with a diameter of 3 that rests above this polar axis. So our circle will be up here. Now if we count the value of 3 above the polar axis, each one of these circles represents a value of 1, or an increase in the radius by 1. So this circle is 1, this circle is 2, this circle is 3. So the graph of this polar equation will look something like this, right? We have a circle, it's above the polar axis, it's split by the vertical axis, and it has a diameter of 3. Okay, so that's this first equation. Now let's look at our second equation, where we have r equals negative sine theta. In this case, our value of a is negative 1, right? So if we're going to graph this equation, note that it's not going to be above the polar axis, it's going to be below the polar axis because that value of a is negative. Now it is negative 1, which means that the diameter of our circle is just going to be 1. So it's going to be a very small circle. So we're just going to be going out to this first circle that represents a radius of 1. That right there is the diameter of our circle. And since the circle needs to be below the polar axis, because that value of a is negative, our graph will look something like this. All right, it's a very small circle, but it has a diameter of 1. It's split by the vertical axis, and it is below the polar axis because that value of a is negative. All right, and so with that, we have now graphed both of these polar equations, and we're ready to move on to our next example. All right, so our next example looks a little bit different. We want to graph r equals 1 minus sine theta by plotting points and using symmetry. So this is one way that you can go about graphing polar equations that are a little bit more complex than some of those basic ones that we looked at in the previous examples. One way that you can go about graphing any polar equation is to try to plot points and use symmetry for your polar equation. And so that's what we're going to do in this example. All right, and so the way this is going to work is we're going to determine if there's any symmetry for our polar equation, and depending on whether there is or not, we'll decide how many points we need to find and plot in our polar coordinate system so that we can take advantage of any symmetry and reflect those points to the other quadrants, and then connect them to get the shape of our graph. All right, and in order to check symmetry for a polar equation, you need to know the following rules. For a polar equation where you have r is equal to some function of theta, if f of theta is equal to f of negative theta, meaning you can plug negative theta into your function and get the same function back, that means you have symmetry about the polar axis. But then if you can plug in pi minus theta into your polar equation and get back the same equation, then you have symmetry about the vertical axis, theta equals pi divided by 2. And then finally, this one we're not going to use that much. This is kind of a last resort if you don't have symmetry in the previous two ways. If you don't have symmetry about the polar axis or about the vertical axis, then you can check this third type of symmetry by plugging theta plus pi into your function and seeing if you get the negative version of your original function. And if that's the case, you then have symmetry about the pole or the origin. Essentially what that means is that you can rotate your graph 180 degrees and it will look the same. All right, but we're not going to use that very often. Typically, you're going to have symmetry about the polar axis, which means that your graph looks the same above the polar axis and below, or you'll have symmetry about theta equals pi divided by 2, which means that your graph looks the same on the right side of the vertical axis as it does on the left side. So now if we go back to our example, let's check those first two types of symmetry. Let's see if this polar equation has any symmetry, and if it does, we'll use that to our advantage when plotting some points to sketch the graph of this equation. All right, so let's start by testing polar axis symmetry. What we want to do is first identify what f of theta is, right? Our function in terms of theta. It's just whatever r is equal to. In this case, that's 1 minus sine theta. So we know f of theta is equal to 1 minus sine theta. And then what we want to do to test polar axis symmetry is plug in negative theta into our equation. And if we get the same function back, then we can conclude that we have symmetry about the polar axis. So if we plug in negative theta, we'll have f of negative theta is equal to 1 minus sine of negative theta. Now, if you're not familiar with your trig identities, there is a way to rewrite sine of negative theta. We know that sine of negative theta is equal to negative sine of theta, right? So we could rewrite it like this. This is equal to 1 minus negative sine theta. Negative sine theta is the same as sine of negative theta. All right, but then if we simplify, we have 1 minus negative sine theta. Those two negatives will cancel out, and we'll have that this is equal to 1 plus sine theta. So what we have here is not the same thing as our original function. We have 1 plus sine theta instead of 1 minus sine theta. So f of theta is not equal to f of negative theta, and so there's going to be no polar axis symmetry. All right, so you can write that down. We have no polar axis symmetry. All right, so we checked that. Now we need to check to see if we are symmetric about the vertical axis. And we can check that by plugging in pi minus theta into our function and see if we get the same function back. All right, so if we do that, we'll have f of pi minus theta. That will be equal to 1 minus sine of pi minus theta. But now in order to simplify this to see if it's equal to the same function, we're going to need to make use of a trig identity, specifically the subtraction identity for sine. If you don't remember what that identity is, it looks like this. Sine of a minus b is equal to sine of a times cosine of b minus cosine of a times sine of b. All right, so if we do that in this case, pi is a and theta is b. So this will be equal to 1 minus sine of pi times cosine of theta minus cosine of pi times sine theta. Okay, now if we simplify, sine of pi is the same as 0. So we have 0 times cosine theta, which is just 0. So this is equal to 1 minus 0 minus cosine of pi, which is negative 1. So we have negative 1 times sine theta. So we're subtracting negative sine theta. All right, but if we're subtracting negative sine theta, that's just going to be positive sine theta. So what we'll have is that this is equal to 1 minus positive sine theta. And now, as you can see, we have the same exact function that we started with. F of pi minus theta is the same as f of theta. So, since that is true, we can say that there is symmetry about theta equals pi divided by 2. Our equation will be symmetric about the vertical axis. Now, the reason why that's important to realize is because now we know that we just have to plot some points on one half of our polar coordinate system, and then we can just reflect that to the other side. We don't have to worry about creating points for the whole graph. We can just work on half of it and then reflect it. All right, so now we can work on that. Let's find some points in one half of our coordinate system that we can plot for this function. Just remember that we are symmetric about that vertical axis. Let's start by making a table of some r and theta values. We'll have theta in this column and r in this column. And to create our points, I'm just going to pick some nice angles for theta that make up 1/2 of our polar coordinate system, particularly angles that will be nice to evaluate in our sine function. All right, so I'm going to start with angles of theta starting at this angle right here, but I'm not going to call it 3 pi divided by 2. Instead, I'm going to work with negative angles from 0 to negative pi divided by 2. Right, so this angle right here is the same as negative pi divided by 2. That's the first angle I'm going to use. So I'm going to have negative pi divided by 2. Then we'll look at this angle right here, which is halfway between 0 and negative pi divided by 2. That will be negative pi divided by 4. So we'll have negative pi divided by 4. Then we'll look at this angle of 0. So we'll have 0. And then I'm going to look at the positive versions of pi divided by 4 and pi divided by 2. All right, so we'll have pi divided by 4 and pi divided by 2. Okay, now let's find some values of r by plugging in these angles into our function. Let's start with theta equals negative pi divided by 2. Sine of negative pi divided by 2 is negative 1. So we're going to have 1 minus negative 1. That's going to be equal to 2. 1 minus negative 1 will be 1 plus 1. So our value of r is 2. Then for theta equals negative pi divided by 4, if we plug that into this function, sine of negative pi divided by 4 is the negative square root of 2 divided by 2. So we'll be subtracting that value. So we'll have 1 plus the square root of 2 divided by 2. So our value of r is 1 plus the square root of 2 divided by 2, which, by the way, that is approximately equal to 1.7. That's the approximate value of that. Then if we move on to our next angle of 0, sine of 0 is 0, so we have 1 minus 0, which is just 1, so r is 1. Then for pi divided by 4, sine of pi divided by 4 is the square root of 2 divided by 2, so we have 1 minus the square root of 2 divided by 2. That will be this value of r. We have 1 minus the square root of 2 divided by 2, and that is approximately equal to 0.3 or 0.29. I just rounded up to 0.3. And then finally, let's look at this angle of pi divided by 2. Sine of pi divided by 2 is going to be 1, and so we have 1 minus 1, which is 0. So r will be equal to 0 for that angle. Okay, now if you wanted to, you could go right from this table of r values and theta values to plotting them in your polar coordinate system, but sometimes you can find it helpful to draw another little graph first that helps relate r to theta, so you can see what happens to r, the radius, as your angle gets bigger. And let me show you what I mean by that. We can draw a little graph here where the vertical axis represents r and the horizontal axis represents theta. And so if this first value right here is theta equals negative pi divided by 2, and then we have theta equals negative pi divided by 4, and then 0, pi divided by 4, and pi divided by 2. Those are our values of theta from our table. We can then plot a point for each of those values of theta given their values of r and see what happens to r as we progress with theta. All right, so the highest value of r that we have here is 2. So I'm going to label that with 2 and then make this 1. Our first angle is negative pi divided by 2, and the radius is 2. So I'll plot that point right here. Then when our angle is negative pi divided by 4, we have 1.7, or 1 plus the square root of 2 divided by 2. So that will be right about here or so. So I'll plot that point right there. And then when theta equals 0, r is 1. So that will be right about here. So I'll plot that point. And then our next angle is pi divided by 4. And that gives us an r value of 0.3. So that's going to be down here somewhere. So I'll plot that. And then we have pi divided by 2 as our last angle, which gives us a value of r of 0. So I'll plot that right there. A value of r equals 0 will be right along this axis. All right, and then what we can do is connect these points, and you can see that as our angle gets bigger, the value of our radius, or r, gets smaller. So when we plot these points in this coordinate system and connect them, we should see r get smaller as we progress from our angle of negative pi divided by 2 to positive pi divided by 2. All right, so let's start plotting these points. Let's start with our first one here. We have an angle of negative pi divided by 2. That will take us to this angle right here. And we have a radius of 2. So if each of these circles represents an increase of the radius by 1, this first circle is a radius of 1, and this second circle is a radius of 2. That means that our first point will be right here, along that radius of 2. And then our next point, we have negative pi divided by 4 as our angle. That will take us to this angle right here. That would actually be 7 pi divided by 4, but that's the same thing as negative pi divided by 4. And so right along this angle here, we're going to be at a radius of 1.7. So that's not quite all the way up to 2, and it's not at a radius of 1, so it's going to be in between these circles, but closer to 2. So right about here or so. So I'll plot our point right there. Then our next point, we have 0 as our angle and 1 as our radius. So an angle of 0 is along this angle, and a radius of 1 will take us right here, right along that first circle where the radius is 1. Okay, then we have pi divided by 4 as our angle. That will take us halfway to pi divided by 2, this angle right here. That is pi divided by 4. And then our radius is 1 minus the square root of 2 divided by 2, or 0.3. So we're not going to be at a radius of 1 along the first circle. We're going to be below that, closer to 0, or closer to the origin. So right about here or so. So I'll plot a point right there. And then we have one more point left. We have an angle of pi divided by 2, which is along this angle right here, and a radius of 0. So that means we're just going to be on the origin because that's where the radius is 0. So we're going to be right there at the origin. Okay, and so now we can stop. We have now plotted points for half of our graph, and since we are symmetric about theta equals pi divided by 2, this angle, we can now reflect those points to the other side and complete our graph. All right, now you could go ahead and just reflect these points to the other side, but what I'm going to do instead is just connect them and then reflect that shape to the other side. So if we connect our points, it will look something like this, and you'll notice that just like we predicted with this graph, that as we progress with our angles, our radius gets smaller. We get closer to that radius of 0 until we finally get there. All right, we started out with a big radius and then it gets smaller, which is what we just did right here. We started out with a big radius and then it gets smaller. Okay, so that's half of our graph. Now we can reflect it to the other side, which means that if we complete our graph, it will look something like this. This right here is the graph of r equals 1 minus sine theta. In fact, this is what we call a cardioid, which is one of our special types of polar graphs. All right, and so that's how we can sketch a polar equation by plotting points and making use of symmetry. You just have to check your polar equation for symmetry and then use that to your advantage when determining what points you want to plot and then making use of that symmetry to make finishing the graph of your polar equation a lot easier. Okay, and so this method that we went through here will work for any polar equation. If you're not sure what shape your polar equation is going to give you when you graph it, you can always fall back to this method of plotting points and using symmetry. However, there are a lot of different special polar graphs that you can identify by looking at your polar equation. And so that's what we're going to focus on with the rest of our examples here. We're going to work on identifying a special type of polar graph by looking at the form of our polar equations and then using what we know about those special polar graphs to sketch the graph of those polar equations quickly. Okay, so here's our first example of sketching the graph of a polar equation by recognizing it to be a polar equation that represents a special polar graph. And now there's 3 different types of special polar graphs that we can recognize here. There are limacons, which are represented by r equals a plus or minus b times cosine theta, or r equals a plus or minus b times sine theta. In both cases, both a and b represent some positive constants. All right, so those are the 2 equations that would represent limacons. Then we have rose curves. That's the second type of special graph. Those are represented by r equals a times sine of n times theta, or r equals a times cosine of n times theta. And for both of these different equations, both a and n represent some constant. All right, and then finally our last type of special polar graphs are lemniscates, which are represented by r squared is equal to a squared times cosine of 2 theta, or r squared is equal to a squared times sine of 2 theta. And a just represents some constant that is being squared. Okay, and so for this first example, we want to sketch the graph of the polar equation, which we have right here, r equals 1 plus 2 times sine theta. And what we want to do is see if we can recognize this polar equation to be one of these 3 types of special polar graphs. Now you'll notice in this case that we have r equals 1, some constant, plus 2, which is a constant, times sine theta. This form of a polar equation doesn't really match the form of a rose curve or a lemniscate, but it does match the form of a limacon. In particular, if you look at this second equation here, r equals a, which is a constant, plus or minus b, another constant, times sine theta. This equation right here that represents a limacon matches our equation right here. All right, and so now we know that this polar equation is going to represent the graph of some type of limacon. And so now that we know that this polar equation represents some type of a limacon, we now have to determine what specific type of limacon it actually represents. And that's all dependent on our values of a and b, the two constants in our equation. If you look over to the sidebar here, these are the two types of equations that represent a limacon, but depending on those values of a and b, we might have one of the following four types of limacons. If a divided by b is less than 1, we'll have a limacon with an inner loop. If a divided by b is equal to 1, then we'll have a cardioid. If a divided by b is greater than 1 but less than 2, then we'll have a dimpled limacon. And if a divided by b is greater than or equal to 2, then we'll have a convex limacon. All right, so in this case, let's identify a and b. We have 1 plus 2 sine theta, so a is equal to 1 and b is equal to 2. So if we look at a divided by b, that will be equal to 1 divided by 2, which is 1/2. And so if a divided by b is equal to 1/2, then that means that a divided by b is less than 1, right? 1/2 is less than 1, and so this polar equation meets the requirements for a limacon with an inner loop. We now have a better idea of the shape of the graph for this polar equation. All right, and so depending on the trig function in our polar equation, a limacon with an inner loop could either look like this graph right here or this graph right here. This first graph is for when we have cosine in our equation, and this second graph is for when we have sine. In this case, we do have sine in our polar equation, so the graph of this polar equation is going to look something like this right here. All we have to do to draw this shape is find some of these points in our polar coordinate system based on the values of a and b from our equation. You can see that the top part of the graph is going to be along that vertical axis where the radius is a plus b. You can also see that the top part of the loop is along the vertical axis at a radius of the absolute value of a minus b, and that this shape is going to cross through the polar axis at the value of a on either side of the vertical axis. So let's find each of those points using our values of a and b. A is equal to 1 and b is equal to 2. We know that a plus b is equal to 1 plus 2, which is equal to 3. So if we count a radius of 3 above the polar axis, if we're assuming that each of these circles represents an increase in the radius by 1, then 1, 2, 3 will take us to this circle right here, but we're going to be along that vertical axis, and so this right here is going to be one of our points. And I'll just label that with 3. All right, now for the top of the inner loop, that's the absolute value of a minus b. So let's do that over here. The absolute value of a minus b will be equal to the absolute value of 1 minus 2, and 1 minus 2 is negative 1, and the absolute value of negative 1 is 1. All right, so that means that a radius of 1 above the polar axis right here along the vertical axis will be the top of our loop. So I'll plot that point right there. Okay, and then finally, we know that our graph is going to cross through the polar axis at the value of a on either side of the vertical axis. So in this case, our value of a is 1. So if we look at our first circle here, our graph is going to pass through 1 on this side of the vertical axis, and then on 1 on this side of the vertical axis. All right, so we'll plot a point right there, and we'll plot a point right there. All right, so that first circle represents a radius of 1. All right, so now we have 4 points plotted that we can use to help us sketch the graph of this polar equation pretty quickly. We know that it's going to be a limacon with an inner loop, and that it's going to look like this. I'm going to start up here. We're going to pass through the polar axis at that point. We're going to come back through the origin, pass through this point to make our loop, come back through the origin, pass through this point along the polar axis, and then come back to the point where we started. Okay, so this isn't a perfect graph, but it is a quick sketch of the graph of this polar equation. This right here is a limacon with an inner loop that is represented by this polar equation. All right, so here's our next example. We want to sketch the graph of the polar equation. We have r equals 3 minus 3 times cosine theta. And so let's see if this polar equation is in one of these forms that will represent a special polar graph. In this case, we have a constant of 3 minus another constant times cosine So just like in our previous example, this looks like it's in the form of a limacon, right? We have r equals a, which is a constant, plus or minus b, which is a constant, times cosine theta. This is the form of our polar equation, so we know that it's not going to be a rose curve or a lemniscate, it's going to be some type of a limacon. Okay, so now that we have identified this polar equation as some type of a limacon, we now need to determine which type of limacon it's going to represent. And that's going to be based off of our values of a and b. Now remember, both a and b are positive constants, so we're going to ignore this negative for now. We'll come back to that in a second. In this case, both a and b are going to be equal to positive 3. So a is 3 and b is 3. And then remember, in order to identify which type of limacon we are working with, we need to take a divided by b and see what that value is. In this case, a divided by b is equal to 3 divided by 3, which is equal to 1. And so that means that we are working with a cardioid. That is when a divided by b is equal to 1. Okay, so whenever you see that the two constants in your polar equation for a limacon are the same, you have 3 minus 3 or 3 plus 3, 2 minus 2, 2 plus 2, 1 plus 1, 1 minus 1, you know that you're working with a cardioid, which is one of the types of a limacon. Alright, and now just like with our previous example, depending on the trig function in our equation, there's two different ways that our cardioid could look. This first graph is when cosine is in the equation, and this second graph is when sine is in the equation. In this case, we have cosine in our polar equation, so our graph is going to look similar to this graph right here. But now what's important to realize is that we don't have 3 plus 3 times cosine theta, we have 3 minus 3 times cosine theta. If this was 3 plus 3, then the shape of our graph would look just like this. However, since it's 3 minus 3, we need to flip this graph about the vertical axis. So instead of having a heart shape in this direction, our heart shape will look something like this instead. All right, it's going to have the bigger end on this side of the polar graph and meet in the origin on this side. All right, but let's find these key points here that we need to label on our graph first. The back end of our graph is a radius value of a plus b. So if we add a plus b, we'll have a plus b, which is equal to 3 plus 3, which is equal to 6. All right, now I don't have 6 circles on this graph here. I have 1, 2, 3, 4, 5, and then I don't have a 6th one. So instead of treating each of these concentric circles as an increase in the radius by 1, I'm going to treat them as an increase in the radius by 2. So this first circle is going to be where we have a radius of 2, the second circle represents a radius of 4, and the third circle will represent a radius of 6. All right, so this third circle is where the radius is 6, and we just found that a plus b is equal to 6, so the back end of our graph is going to have a radius of 6. Now remember, we do need to flip this graph to the other side because we have negative cosine, so this back end of our graph will be on the other side. It's going to be right here in this polar coordinate system. Okay, so right here is one point that's going to help us graph this equation. Now the other 2 points that we can plot are going to be the values of a along the vertical axis. In this case, a is equal to 3, and so we can plot a point at the value of 3 above the polar axis and below the polar axis along that vertical axis. And so the radius value of 3 is going to be in between this circle and this circle, right? If this circle is a radius of 2 and this circle is a radius of 4, then in between there would be a radius of 3. So we'll have 1 point here and 1 point here. Okay, so now we can draw our graph. Our cardioid is going to meet at the origin, but it's going to come out, pass through this point, go through this back end point, come through this point, and then meet back at the origin. That right there is a sketch of the cardioid represented by this polar equation. All right, next up we want to sketch the graph of this polar equation. We have r equals 2 times cosine of 6 theta. Now in this case, this polar equation is not in the form of a limacon, right? We don't have a constant plus a constant times a trig function. We just have a constant times a trig function of 6 times theta. And so this polar equation is going to match with the form of a rose curve, right? Rose curves can be represented by r equals a, some constant, times cosine of some value n, another constant, times theta. This is exactly what we have right here. except a is equal to 2 and n is equal to 6. So I'll write that down. A is equal to 2 and n is equal to 6. Okay, so we know this polar equation is going to represent a Rose curve of some kind, and that is given that that value of n is greater than or equal to 2, which in this case it is. But based on that value of n, whether it's odd or even, is going to determine how many petals our Rose curve has. If our n is odd, we'll have n petals, but if our n is even, we'll have 2 times n petals. In this case, our value of n is 6, and 6 is even, so we're going to have 2 times that value of n as our number of petals that we need to graph. So in this case, we'll have 2 times 6, which is equal to 12, so we're going to have 12 petals, okay? And that's because n is even. Now, when you have a polar equation that you recognize to be a Rose curve, and the trig function is cosine, not sine, this is how you want to sketch the graph of that Rose curve. For cosine, it's pretty simple. You start by drawing one petal along the polar axis on the right side, assuming that the value of a is positive. If it's negative, then you have to reflect the whole thing to the other side, so you would start on the left side. But in this case, our value of a is positive. It's positive 2. So we're going to draw our first petal on the right side of the vertical axis along the polar axis, and it's going to reach out to a radius of that value of a. In this case, that means the radius that each of our petals will reach out to will be 2. Now in our polar coordinate system here, I'm going to say that every second circle is a unit of 1. So this second circle will be a radius of 1, and the fourth circle will be a radius of 2. Okay? That way we can draw our Rose curve pretty big here. And what we want to do is draw that first petal in that location, and then distribute the rest of our petals evenly. We know that we need 12 petals, so what we'll do is we'll draw one right here, that's where we will start, and then we'll just distribute the rest of them around the polar coordinate system in an even fashion. And so I'll draw the first petal. I'll start at the origin, come out to this value of 2 for our radius, and then come back to the origin. All right, so I drew this first one here, and now what we need to do is draw 11 more. We need to distribute them evenly throughout this coordinate system. But now since we have an even number of petals, this isn't too bad. What we can do is draw another petal along each side of the axes, right? So we'll have another petal on this side that comes out to a radius of 2 and comes back in. We'll also have one along the vertical axis in this direction, and we'll have one in the other direction. All right, each of them reached out to that radius of 2. Okay, so now we have 1, 2, 3, 4 petals. We still need 8 more. So now we just have to distribute those 8 petals evenly throughout the rest of the graph. And so what we can do is ask ourselves, how many petals do we need to draw in each quadrant? Well, if we have 8 more to draw, we can put 2 in each quadrant, since there are 4 quadrants, and that will give us the other 8 petals that we need. So we're going to draw 2 petals in between each of our petals along the axes. And just remember that this is a sketch, so this isn't going to quite be perfect, but I'm going to do my best here. It will look something like this. I'll draw one petal here, then we'll have another petal in between there, then we'll have one here, and then one here. We'll have one here, and then another one here. Remember that with each of these petals that you need to reach out to that circle that represents a radius of 2, they all need to be the same size. And then I'll draw my last 2 petals here. We'll have one here, and then one here. All right, and so this right here is the graph of this polar equation. This is a Rose curve with 12 petals when working with the cosine function. All right, and so just to count to make sure that we have all of them, here's 1 petal, 2 petals, 3 petals, 4 petals, 5 petals, 6 petals, 7, 8, 9, 10, 11, 12. All right, so there's all 12 petals. We know we didn't miss any. And now we're ready to move on to our next example. All right, so here's our last example. We want to sketch the graph of this polar equation, r squared is equal to 9 times sine of 2 theta. All right, so comparing this polar equation to these other equations here that represent special polar graphs, since we have r squared is equal to 9 times sine of 2 theta, that's a pretty big indicator that you're going to be working with a lemniscate, where each of those two equations deal with r squared. All right, another way you might see that is r is equal to the square root of a squared times cosine of 2 theta, or the square root of a squared times sine of 2 theta. Okay, but this polar equation is in the form that represents the graph of a lemniscate. Alright, now unlike limacons and rose curves, lemniscates are pretty simple to graph. They're not too complicated. It will either look like this graph right here when your trig function is cosine, or it will look like this graph right here when your trig function is sine. Now it is important to know that if your value of a squared has a negative sign in front of it, that these two graphs will look different, and I'll just briefly show you what that looks like. If you had a negative sign in front of a squared times cosine of 2 theta, this graph would instead look like this. It would be along the other axis. And if you had a negative sign in front of this a squared times sine of 2 theta, then this graph will look something like this. All right, so it does change a little bit. In each case, both of them are just being reflected about the pole or the origin. Essentially, we're just rotating the graphs 180 degrees. All right, so that's what you would do if you had negative a squared times cosine of 2 theta or negative a squared times sine of 2 theta. But that's not what we have in this case. Instead, we have r squared is equal to positive 9 times sine of 2 theta. And so in this case, a squared is equal to 9, which means that a is equal to the square root of 9, which is equal to 3. And that value is important because the value of a measures the distance across each of those loops on either side of the lemniscate. Now in this case, we're working with sine, so our graph is going to look like this down here, where we have r squared is equal to a squared times sine of 2 theta, right? We're not working with cosine, we have sine. And so our graph will look like this. We just have to measure that distance of a so that each of our loops will reach out to that radius value of a. So in this case, a is equal to 3. So if we treat each of these circles to be a unit of 1 for the radius, the first circle will be a radius of 1, the second circle will be a radius of 2, and the third circle will be a radius of 3. So both of those two loops that we have to draw are going to reach out to the third circle. Okay, so now let's draw our graph. I'll start at the origin here. We'll reach out to a radius of 3, come back, and then we'll loop around, reach out to 3 again, and then come back in. Okay, so both of those loops reach out to that value of 3 for the radius. And so that's really all there is to sketching the graph of this polar equation. Lemniscates are pretty simple, and so at this point we're pretty much done. This is the sketch of the graph of this polar equation. All right, so hopefully these last few examples are pretty helpful in showing you how to quickly sketch the graph of polar equations if you can recognize the form of those polar equations as being the special types of polar equations that represent special polar graphs. And so that includes the different types of limacons, the different types of rose curves, and the different types of lemniscates. Okay, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.